One of the most helpful linear transformations is actually the left multiplication linear transformation. It goes from Fn to Fm, and it's just multiplying by a matrix on the left. Okay, so you can think about that as a linear transformation. For instance, if A was a 3 by 2 matrix, right, 3 rows, 2 columns, so 1, 2, 3, 4, 5, 6, what would that act on? It would need to act on a length 2 vector. So let's pick the first canonical basis element. So row column equals 1, second row column equals 3, third row column equals 5, and you can see that it comes out in F3, just like you'd expect. And there are a bunch of properties. So if A is an m by n matrix, LA is that linear transformation, and it is indeed linear. That's pretty straightforward to see, and you get all of these properties. So the matrix representation of LA in terms of the canonical bases beta and gamma is A itself. Left multiplication by A is the same as left multiplication by B if and only if A is equal to B. Left multiplication is additively linear, it scales. If you have any linear transformation from Fn to Fm, you can actually describe it by left multiplication by the matrix representation of T in terms of the canonical bases. You can multiply on the right by a matrix, and that works with left multiplication. If the matrix is square, left multiplication by the identity is the identity on Fn. Now, C and F, the proofs are homework. But we are going to talk about the justifications for A and B here. So let's try and prove A. Okay, so what is the matrix representation of LA in terms of the canonical bases? Well, we need to ask, hey, what's LA of EI? Well, that's left multiplication by A. And EI has zeros except for in the ith position. So what will that call out? That will pull out the ith column of A. So we'll get something like A1I down to AMI. Make sure you believe that from there. Well, then what are we supposed to do when we're looking for the matrix representation? I need to get the coefficients of representing this in the basis of the codomain, right? So that's EI to EM in the codomain. But how do you get an A1I there? You multiply A1I times E1, and you go through. And so your coefficients are just the entries in this column, MI, right? Well, and then the way you make the ith column of LA, the matrix representation of LA in terms of beta gamma, is it's just those entries, right? So it's A1I down to AMI, right? Oh, but wait, so the ith column of A is exactly the same as the ith column of that. So therefore, the matrix representation of LA in terms of the canonical bases is just A itself. And that's what we were pointing out. Now, once you have that property, think about what that means for something like part B, left multiplication of A is equal to left multiplication of B. Well, the only way two linear transformations can be the same is if they take the same values on every basis element in the domain on some basis. Well, if they take the same value on every basis element, another way to see that would be take a basis, and the matrix representation had better be exactly the same in that basis. So, okay, these are the same if and only if their outputs for each basis element are exactly the same. But wait a second, what was this by part A? Well, this was exactly matrix A. That was exactly matrix B. So these things really fit together quite well. Hope that's helpful.